So very good morning. So we were discussing about Unit 2. So Unit 2 deals with embedded networking. So how you are going to interconnect the various controllers, that is what we are seeing. So in this we have concluded that we will go only with serial communication. Parallel communication we doesn't talk with respect to networking. The reason is you require more number of cables. Okay, so that is not practically possible. Investing that huge amount is little bit waste. So we go only by serial communication. So today let us see two types of serial communication protocol. One we are going to see about CAN bus. Another one we are going to see about I2C. These two are very widely used in industries. We will see what is the advantage of the both. Okay, both has some advantage and both has some disadvantage, but we will see about CAN bus and I2C today. Okay, so CAN we call it as controller area network. So this has been introduced by Bosch. You might have all thought that Bosch is an industry which deals with the speakers manufacturing, but it is they are pioneers in embedded system. So they take care of automobile embedded system also. Okay, so Bosch is a company which deals with all types of embedded system related to automobiles. So CAN bus is a vehicle bus standard designed to allow microcontrollers and the device to communicate with each other. Okay, so for the communication purpose in vehicles we use this CAN bus. So CAN bus is nothing but a protocol which tells about how you are going to transfer the data between the different controllers in your vehicle. It is message based protocol, which means you don't have any synchronous data transfer. It is only asynchronous data transfer. Whenever each controller in the want to communicate, it will take off the entire path and it starts to communicate. Okay, so a best example to understand this CAN is it is like radio broadcasting. So you will send the message and will be received by all the receiving end, and whoever wants that message will pick, others they will just omit. For example, there are so many FM broadcasting. I think we all know, like you have Suryan FM, Radio Mirchi and all other like 101, 104. There are so many FM channels. Are you at the same time in your home radio, you are not listening to all the channels, so you tune to any one particular channel and you start listening it. Same way it is for CAN. So CAN, all the controllers in your automobile can behave like an master, and at a time only one master will send the data, and that is sent data will go to all slave, but the slave which requires the data alone will try to pick up and then use it for its own purpose. So that is how CAN is going to work. So this was introduced, I told it was introduced by Bosch in 1986. It is mainly developed for automotive applications. Then it has been standardized in 1993. Once it has been standardized, anyone in the world can use that particular protocol. So they have standardized as ISO 118981. CAN comes with two different standards. One is CAN 2A and CAN 2B. That CAN 2B is the extension version of CAN 20A, where CAN 2 you have a separate like 29-bit identifier and 11-bit identifier. So the extended version you can connect more number of devices. That's all. I repeat, just I will say what is CAN. So CAN bus is nothing but it is similar like your radio channel broadcasting. So at an instant there are so many channels being broadcasted in air, but all that signals are available on air, but you tune to any one particular channel and try to get the information. So similar way in an automobile industry, all the microcontrollers will try to send that data, and the person who want to receive alone will try to get the data and others omit. Okay, but at a time only one master can communicate. So this type of protocol is off duplex, which means at a time only one person can communicate. All other person can receive, but all other person cannot transmit at the same time. Okay, at a time anyone can do, and it is comes on asynchronous. So whenever you say asynchronous, there won't be any clock in your transmission. So it is only by number of bits you try to send it as a packet and it is been transmitted. Okay, so that is what. And when you see one example for CAN bus, so you have a common bus. So in this common bus you are able to connect like ABC, air condition unit, engine control unit, transmission unit and battery unit, seat position, instrument panels and suspension. Okay, now suspension and all is not mechanical suspension, all are hydraulic, or even now we have moved to air suspension. So for the operation of suspension itself you need a separate controller, and already I have told what is ABS. ABS is for braking in your automobile. So braking is when object is at a very fast and when you want to bring it to rest, you cannot apply the brake suddenly. So for that you have a separate control unit which is controlling the brake. Okay, and air condition, in nowadays I have a digital meter inside my cabin where I can see what is the present temperature inside, and I can even set to a temperature similar what you do in your AC. So keep it in 22 degree or 23 degree. So a separate controller will be working on it. Seat position is also automatic. Now you can sit and press a button and try to pull the seats back, front. You can just adjust the top portion or the bottom portion, whatever you want to do. Then comes your transmission. Transmission is your gear changing from first gear to second gear, third gear, fourth gear. Everything is now automatic. So that requires a separate controller. Then battery management system. Now the systems are with hybrid. So the battery management will have a separate controller unit, and that controller unit will try to control your battery level, monitoring and transmitting all. And finally comes to engine. So in olden days only this was there in your automobile. Your automobile has only engine. Now that engine is only a secondary. All you have so many controllers other than this particular engine of your car. Okay, so cables are, it is a twisted pair cable, so you use only 2 cables for data transmitting inside your this. So twisted pair cables are used to get higher speeds. The bit rate of the data transformation is high for short transmission distance and long transmission distance. Bus length is for, when you have a bus length of 40 meters, you can have a maximum speed of 1 Mbps. So this is the maximum speed for CAN protocol. So when the meters is increasing, automatically the bit rate will come down. And if you, finally if you are in your automobile, you can have maximum of 500 meters. So assume the cable is running. So cable will be running from engine. So everything will be connected to the common bus. The length of this bus, this from this end to this end, will be around 6 meters. Worst case I am saying, that is whenever you go for embedded system for a very big vehicle. It's a vehicle nowadays, you have very big transport carrying vehicle with more than 20 wheels to 30 wheels, where you will have this length wire, whereas in your normal car not more than 40 meters. Okay, so now let us come how the data is being sent. The thing which you have to understand very clear is this is asynchronous data transfer. So when you say asynchronous data transfer, there won't be any clock pulse, and since you are sending the data, initially you will have a startup frame. So I have told that all the controllers inside your automobile can behave like a master. So whenever any person want to communicate, he will behave as a master, and then he will try to transmit. Similar to your, don't forget, try to remember your radio channel. So whoever has a transmission unit, he will transmit. Okay, so similarly here, first whenever you start your transmission, first should be of SYF. SYF is for startup frame. So now assume that, come to this picture. Now you can see how many controllers are here. See, this is a separate controller, controller 2, controller 3, controller 4, 5, 6, 7, 8. So there are 8 controllers at a time. Among this 8 controller, anyone can be a master. So try to listen. So when suspension want to talk anything with respect to engine, or engine requires any data from suspension, then this engine will try to make us a master, and it will try to transmit data, and that data will be received by all but others will reject, and only the suspension will observe it, and it will try to do the request what has been sent by engine control, and again this will become like now master, and he will transfer the data, and that data will enter into all controllers, but that controllers will identify that the information is not required for it, and it will directly engine control alone will receive it. So that is the thing here. So at a time it is half duplex I have told, so bidirectional communication is not possible among the masters available. See here, 1 2 3 4 5 6 7 masters. In CAN you don't have anything called as slave, everything is only master here. But the thing is, at a time anyone can be a master, that's all cannot be a master at the same time. So if the suspension is going to talk, so you may imagine what is there in suspension. Suspension is like, if the air pressure is low in the tire, automatically the suspension will expand, and this will tell to the engine that there is less amount of air or even chance for puncture. So what will happen, this will go here, it will go to engine control, then the main controller or the main embedded in engine control will identify, and again it will send it to the dashboard saying that air pressure is low. Okay, something is there on the left side wheel, so you check whether air pressure is low, or is there any puncture has occurred, or is there any bend in your wheel. Okay, everything will be indicated by this suspension. But at the time when the suspension is discussing anything, only that suspension will behave like a master, all other fellow will behave like a slave. So all other person will receive, only the person who is going to send will be a master. Okay, so that is what with respect to CAN. So when you see the data format, so let us assume that now ABS is going to communicate. So if the ABS is communicate, ABS will first tell about start of frame. They will say that I am going to start. And then this identifier is here is not the address, it will tell the content of the message. So what is there inside. So each and every content can be indicated. So this will tell about the content of this, and then comes your remote transmission request. So when you want to transmit, then first you have to set SOF, then you have to tell what this the content is. So you have to say content is from ABS. So then RTE, then DTE is identifier extension. Who is going to identify? He will have his own identifier addition. Then comes your DLC, data length code. This I will tell it is an 8-bit data or 16-bit data or 32-bit data or 42-bit, whatever, 64-bit. Okay, that will be mentioned in your DCL, data length code. So once this been read by the person, he will know what is the data length. Then once data is over, then CRC check. CRC is cycle redundancy check. I think you might have studied this. So this fellow is going to send the person who is going to receive, if he sees what is DLC. So DLC will tell about it is whether 8-bit or 16-bit it will tell. So if it is saying it as 16-bit, then the CRC check will do nothing but it will check how many data is there. Okay, how many data are there. So if this match with this data which is arrived, then cycle redundancy will pass, which says that there is no error. Then it will give acknowledgement. So I will explain here. So ABC is there, this is going to send to the control engine. So it will have an identifier saying that the data is coming from ABS. Automatically the main controller will understand whenever ABS is sending something, it will say content from ABS. See, this content will go to suspension, air condenser, instrument panel, seat position, transmission and battery. It will go to all controllers, but all that controller will reject, saying that the information is not required for them. So who will receive? The engine part will receive. Now this ABS has to tell a start bit. That start bit is read by this fellow. Then he will tell about how many bit of data I am going to send. Then he will send the data. Finally this fellow who is having CRC will check with the number of bit and number of bit received. So once that is been done, it will give acknowledgement stating that what all you have sent I have received, and then he will release end of frame. Only after this end of frame, any other person can behave like a master. So until that, no other person is allowed to transmit. So till that instant, all other fellow has to wait only, and after this being released, that is EOF is being released, end of frame is released, then any other person can start. So IFSC is intermission frame space, minimum number of bits separating consequent image, then it will go to ideal stage. Once it has gone to ideal stage, any other master now can start the work. So data formation is, I have to divide my data into frames. So each and every frame will have a unique content, what is the content it is having, and then it will be sent. So message are distinguished by message identifier. The identifier is unique to the network and defines the content and the priority of the message. Then start of frame is a logical 0 indicating. So whenever I have last class I have told either you will have 1 or 0. So logical 1 we will not use. When you say you are going to start, I will bring it to logical 0. Then attribution field, it is 11-bit identifier. Then control bit, I have told what and all comes under control bit. So all this comes under control bit. I am going to control. So that is why it is called a control bit. Then data field. Data can be from 0 to 8-bit data. If you want, you can send more data also. That depends upon the capability of the person who is going to receive. Then CRC field is cycle redundancy check. It is a 15-bit cycle redundancy check code. It is an 1 bit. So it is for checking how many bits you are going to send. Acknowledge bit and end of frame. So remote frame is, you will first start, send the identifier, then you will field, then all control field you will send, then CRC field you will send, then finally acknowledge. So this is for the end of frame. Then error is, if there is any error is occurring, you have a separate flag, that flag will rise. Overflow is, if you are sending beyond the capability of receiving, then you will not be able to receive, so you will send overflow flag is occurring. Now let us see a small video presentation. So that video presentation, if you see, then you can able to identify, you can understand it better. Okay, so you can kindly watch this video. He will be explaining about the CAN bus.
CAN bus explained. A simple intro. Struggling to find an intro to CAN bus written in layman's terms? So were we. Therefore, we decided to launch a series of simple CAN intro articles written by one of our non-engineers to make sure it stays simple. Enjoy. What's CAN bus all about? Imagine that your car is like a human body. The controller area network system, CAN bus, is the nervous system, facilitating communication between all parts of the body. Similarly, nodes, or electronic control units, ECU, are connected via the CAN bus, which acts as a central networking system. In an automotive CAN bus system, ECUs can, in example, be the engine control unit, airbags, or the audio system. A modern car can have up to 70 ECUs. This is where the CAN standard comes in handy, as it allows ECUs to communicate with each other without complex, dedicated wiring in between. In turn, this allows for several features to be added via software alone. An example, electronic gearbox control. Indeed, that is the primary purpose of CAN, to allow any ECU to communicate with the entire system without causing an overload to the controller computer. But why is CAN so popular? 5 key reasons. 1. Low cost. ECUs communicate via single CAN interface. In other words, not analog signal lines, reducing errors, weight, cost. 2. Centralized. The CAN bus system allows for central error diagnosis and configuration across all ECUs. 3. Robust. The system is robust towards failure of subsystems and electromagnetic interference, making it ideal for, an example, vehicles. 4. Efficient. CAN messages are prioritized based on IDs so that the highest priority IDs are non-interrupted. Critical. An example, vehicles. 5. Flexible. Each ECU contains a chip, allowing it to receive all transmitted messages, decide relevance, and act accordingly. This allows easy modification and inclusion of additional nodes such as CAN bus data loggers. The CAN bus history in short. Pre-CAN car ECUs relied on increasingly complex point-to-point wiring. In 1986, Bosch developed the CAN protocol as a solution, releasing it at a SAE Congress. In 1991, Bosch published CAN 2.0 Inclusion, CAN 2.0A 11-bit, and CAN 2.0B 29-bit. 1993. CAN is adopted as international standard, ISO 11898. 2012. Bosch released the CAN FD 1.0, aka CAN with flexible data rate. Today, almost every new European car comes with a CAN bus system, and it is used broadly in trucks, buses, industry vehicles, ships, planes, and industrial automation. Further, more exotic uses include drones, radar systems, submarines, or even prosthetic limbs. Looking ahead, the CAN bus system will stay relevant, and most likely even more so with the rise of, example, cloud computing, Internet of Things, IoT, and autonomous vehicles. What does a CAN message look like? To understand how the CAN bus system works, let's break down the messages sent over the network. The 11-bit identifier, CAN 2.0A messages, look similar, but with shorter CAN IDs. The 8 key parts of a CAN message are as follows. SOF. The start of frame is a dominant 0 to tell the other ECUs that a message is coming. CAN ID contains the message priority, as well as functional address, an example, RPM, wheel speed. RTR, the remote transmission request, allows ECUs to request messages from other ECUs. Control informs the length of the data in bytes, 0 to 8 bytes. Data contains the actual data values, which need to be scaled or converted to be readable and ready for analysis. CRC, the cyclic redundancy check, checks data integrity. ACK, the ACK slot indicates if the CRC process is okay. EOF marks the end of the CAN message. That's a lot, but only 3 are practically relevant in most data logging scenarios: the CAN ID, the control, and the data field. This is also why you typically only see these in CAN bus data output. CAN provides the basis for communication, but not a lot more. For example, the CAN standard does not specify how to handle messages larger than 8 bytes or how to decode the raw data. Therefore, a set of standardized protocols exists to further define how data is communicated between ECUs of a given network. Some of the most commonly encountered standards include SAE J1939, OBD2, and CAN Open. SA J1939. This is the standard in vehicle network for buses, trucks, and other heavy-duty vehicles. All J1939 messages rely on the extended 29-bit CAN identifier. Further, J1939 data parameters, an example RPM, vehicle speed, are identified by a suspect parameter number, SPN, which are in turn grouped in parameter group numbers, PGN, containing 1 plus SPNs. With this standardized structure, CAN messages from example buses and trucks can be scaled and decoded into readable data using parameter tables from the J1939 standard. Further, several standards are derived from J1939, including, an example, the Fleet Management System, FMS, which is freely available and included in Canvas. For more information, see our simple intro to J1939 or our J1939 ID to PGN converter. OBD2. Onboard Diagnostics, OBD, is a self-diagnostic and reporting capability that, an example, mechanics use to identify what is wrong with your car. The OBD2 standard specifies a number of standardized diagnostic trouble codes, DTCs, which can be retrieved by a CAN logger or diagnostics tool for any vehicle. But what makes OBD2 really interesting? OBD2 supports data on many basic real-time parameters, an example, vehicle speed, RPM, fuel consumption. This means that OBD2 is also used for an example, real-time vehicle telematics or post-analysis using CAN data loggers. Applications include vehicle fleet management, fuel optimization, proactive vehicle diagnostics, and more. To log OBD2 data, the CAN logger must request the data by submitting pre-specified CAN frames with specific parameter IDs, PID, to the CAN bus. When using the CAN logger X000, this can easily be configured in Canvas. For basics on OBD2, check out our simple intro to OBD2, or check our practical guides to logging OBD2 data or streaming it in Wireshark. CAN Open. CAN Open is used widely, an example, industrial automation applications. It builds on CAN in terms of physical layer, an example, lines used, voltages, and the data link layer, an example, utilizing a CAN frame message based on protocol. In practice, this means that a data logger, like the CAN logger X000, is able to log data from CAN Open applications, though the method of X post data conversion will vary depending on the specific application. Our Intel page contains several intro articles, uses cases, and guides. Let us know if you have more suggestions for the series. Interested in our products?
So I think we can conclude that what is a CAN bus is. So a CAN is ideally suited for application like where you connect more number of controllers together and there is no synchronous data transfer, so anyone can operate at whatever speed it can. So it is not that this you are putting 5 or 6 controller, all that controller has to operate on same clock. That is not required, because your suspension unit will have a controller which may operate at a particular speed, and there is no necessity that all must be of same operating speed. So you can connect all that controllers to a common bus and you can operate your CAN protocol. So that is the main advantage of this CAN. So I think we can even stop with this today, and then we will start I2C on next class. Okay, thank you students.